Hey everyone, welcome. Today we are diving straight into the very core of modern tech in this explainer. We're going to explore how incredibly basic electronics are masterfully transformed into the thinking, remembering machines that we literally rely on every single second of our daily lives. We're talking about combinational circuits and synchronous sequential logic. Now, I know that sounds like a bit of a mouthful, but stick with me. By the end of our time together, you'll see exactly how these concepts basically build a digital brain from scratch. It's the ultimate question, isn't it? When you strip away the screens, the sleek cases, and all the flashy software, how does a machine actually think and remember? Well, we're embarking on a pretty high-stakes engineering journey today. We're going to pop the hood and look at a computer's foundational logic. We aren't just talking about wires and silicon here. We're looking at the exact, microscopic mechanisms that allow a machine to process information in the absolute blink of an eye, and then crucially, hold on to that information for the future. So here's our roadmap for building this digital brain today. We'll start with the basics of combinational logic, move into routing and decoding data, and then dive into flip-flops and creating digital memory. After that, we'll tackle computer arithmetic and algorithms and wrap it all up with your digital design toolkit. To kick things off, you have to understand that there's a grand divide in digital electronics. Everything we talk about today falls into one of two buckets. First, we have combinational logic. This is immediate action. The inputs change and boom, the outputs change instantly. There is absolutely no memory involved. A combinational circuit only knows what is happening right this very second. On the other side, we have sequential logic. This is clock-driven, and most importantly, it has memory. It relies not just on what's happening right now, but also on what happened a microsecond ago. This duality is really the secret sauce to all of computing. All right, part one, the basics of combinational logic. Think of these foundational circuits as a machine's immediate involuntary reflexes. We've got half and full adders, which, you guessed it, literally add binary numbers together instantly. We've got half and full subtractors for taking numbers away, binary multipliers that can immediately scale those numbers up, and combinational circuits specifically designed as code converters, translating one type of binary language into another. The absolutely crucial point here is that these components act like a highly efficient speed-of-light calculator. You punch in the numbers and the result is generated purely based on that current input, with zero knowledge of the math problem you solved 5 minutes ago. Which brings us to a really brilliant piece of engineering, the BCD, or Binary Coded Decimal Adder. It's a specific type of combinational circuit that beautifully bridges the gap between simple binary logic, the ones and zeros the machine loves, and the base 10 decimal numbers that we human beings actually read and understand. Digging into the BCD adder on your own is a fantastic way to grasp how these combinational circuits can be custom designed to translate cold machine logic right into our human reality. Moving right along to part two, routing and decoding data. So now our system can do some basic immediate math. But we quickly run into a brand new problem: traffic management. Imagine millions of bits of data flying around our circuits like cars at rush hour. We need a way to manage that flow. Enter the multiplexer. You can think of a multiplexer exactly like a digital traffic cop. It stands at a super busy intersection where multiple lanes of input data are rushing in, and it seamlessly routes them onto a single, high-speed output highway. Depending on the control signals it receives, the multiplexer decides exactly which lane of data gets to move forward at any given microsecond. It's elegant, it's incredibly efficient, and it is absolutely essential to preventing complete data gridlock. Of course, our digital traffic cop doesn't work alone. To manage this massive flow of immediate data, we rely on a whole suite of combinational circuits. We have demultiplexers, which do the exact reverse, taking a single lane of data and distributing it out to multiple outputs. We use encoders to compress data and decoders to unpack it back into its original form. And we use magnitude comparators, whether they're 1-bit or 2-bit, to instantly look at two numbers and tell the system, hey, is A greater than B, less than B, or equal to B? Together, this entire suite of circuits keeps the data moving exactly where it needs to go. Which brings us to part three, flip-flops and creating digital memory. So, our digital brain has its reflexes, and it can route traffic like a pro. But to truly be a computer, it has to remember. We're now adding the critical dimension of time, and that brings us to one of the most brilliant inventions in human history, the flip-flop. It is quite literally the basic atom of computer memory. Unlike our combinational circuits that forget everything the moment the input changes, a flip-flop is a synchronous sequential circuit capable of actually storing a state, a 1 or a 0, over time. It locks that memory in place until a specific clock pulse tells it to change. This one simple ability to hold a state is what allows a computer to run software, save your files, or remember your password. Now, this builds into a pretty complex memory architecture. There isn't just one type of flip-flop. Engineers have developed an entire family of them. We've got the SR, the D, the JK, the highly stable JK master-slave, and the T flip-flop. Engineers use truth tables to understand exactly what output a flip-flop will produce based on its inputs. But when they're actually designing a circuit from scratch, they use excitation tables. The excitation table works backward. It tells the engineer exactly what inputs they need to apply to force that flip-flop to change into a desired state. It's basically the ultimate control manual for digital memory. But here's where it gets really cool for a digital designer. You aren't limited by the hardware you have on hand. A really critical skill in sequential logic is understanding flip-flop conversion processes. This means you can logically wire, say, a basic D flip-flop to behave exactly like a JK flip-flop, or vice versa. Identifying these conversion processes gives engineers just incredible flexibility to build complex memory systems using whatever logical building blocks happen to be available to them at the time. All right, part 4, computer arithmetic and algorithms. Okay, so we have our instantaneous combinational reflexes and our sequential flip-flop memory. Let's combine them to do some heavy lifting. To solve complex binary multiplication, computers don't just use massive, highly inefficient combinational multiplier blocks. They actually use a sequential method called Booth's algorithm. Here's how it fundamentally works. Step 1, the system initializes the values in its registers. Step 2, it checks the specific bit conditions of the numbers being multiplied. And Step 3, based on those bits, it intelligently decides whether to shift the data, add, or subtract. By looping through these steps, Booth's algorithm elegantly handles binary multiplication, especially when dealing with negative numbers, using far fewer hardware resources than a brute force approach. It's just really smart, iterative arithmetic. And what about division? Well, division is notoriously hard for a computer. To tackle this, engineers rely on 2 major algorithms. First, we have the restoring division algorithm, where the system basically takes a guess, subtracts, and if it went too far, like if the result goes negative, it simply restores the original value and tries again. Then we have the non-restoring division algorithm. This is a slightly more advanced, faster approach that skips that restoring step entirely by cleverly adjusting the next operation based on whether the previous result was positive or negative. These algorithms really represent the absolute peak of how a computer uses both logic and memory together to solve hard math. Finally, part 5, your digital design toolkit. Let's pull back for a second and look at the big picture. You've just unlocked a massive engineering toolkit today. You now know how to apply Boolean algebra to represent complex expressions using combinational circuits. You understand how to actually design those circuits using logic gates. You can discern the distinct functionalities of different flip-flops and identify exactly how to convert them. And you can apply the fundamentals of Booth's algorithm to solve binary number multiplication. Think about it. You aren't just looking at a computer anymore. You are looking at the foundational blueprint of how it actually operates. But if there's one golden rule to take away from this entire toolkit, it's this: validate your circuits using truth tables. In the real world, an unverified circuit is a deeply dangerous circuit, whether that logic gate is going into a video game console, a medical pacemaker, or the navigation system of a deep space rocket. Verifying the logic with a truth table ensures that when the system faces a critical input, it will not catastrophically fail. Validation is truly what separates theoretical ideas from reliable, life-saving engineering. So the next time you're marveling at an incredible new piece of artificial intelligence or getting lost in a massive open-world game, I want you to remember this. Beneath all the beautiful graphics and the ridiculously complex software, the whole shebang ultimately boils down to the simple combinational logic gates and sequential flip-flops that we just went over today. You now understand the language of the digital brain. The only question left is, what will you build next? Keep exploring, and I'll catch you next time.